In this video, we introduce the A* search algorithm, which is used, for example, in GPS navigation to find the quickest path through a massive network of roads. To search for a path, we first divide the environment into a grid of discrete cells. We identify which cells are walkable corridors, allowing movement through the space. We then define the solid obstacles, which block movement and must be avoided. Within this grid, we mark the starting point in green, where our journey begins. Finally, we set our destination target in pink, framing the route we must find. Unlike humans, who can see the whole map at once, a computer must inspect the grid one step at a time. If the computer blindly tries every possible route, the number of choices explodes, grinding the system to a halt. To solve this efficiently, we need a smart search algorithm that finds the shortest path without checking the entire map. Let's compare the classic blind search, called Dijkstra's algorithm, with the optimized A* search. Dijkstra's algorithm searches blindly, expanding outward in all directions like a ripple in a pond. While it is guaranteed to find the shortest path, it wastes immense power exploring areas facing away from the target. A* improves this by using a heuristic function to estimate the remaining distance to the target, guiding the search frontier. To balance past progress with future estimates, A* uses a simple but powerful scoring formula. To guide the search, every grid cell is evaluated using a total cost score, the F-score. To calculate this total F-score, we first use the G-score, which represents the actual path cost already spent to reach this cell from the start. To complete the equation, we add the H-score, a heuristic estimate of the remaining cost from this cell to the goal, such as a straight line. By combining the G-score and H-score to form the total F-score, A* balances past cost and future estimates to focus directly on the most promising directions. To find the shortest path, A* systematically organizes the cells it discovers into two groups, the open set and the closed set. We begin the search by placing only the starting cell into the open set. From here, the loop begins by selecting the cell with the lowest total cost, which, in this first step, is the starting cell itself. For each walkable neighbor of this selected cell, we calculate the G-score, the actual distance traveled from the start. We then estimate the H-score, the remaining distance to the goal, using a straight-line heuristic for each neighbor. Adding these two values together gives us the total estimated F-score for each neighboring cell. These neighbors are then added to the open set as new candidates for future exploration. With its neighbors evaluated, the starting cell is moved from the open set to the closed set, ensuring we never check it again. From here, the loop simply repeats, constantly selecting and expanding the lowest score candidate in the open set until we reach our destination. The real magic of A* happens when the path is blocked by walls and obstacles. When encountering a wall, the straight line guesses temporarily increase, forcing the search to spill around the edges. Once the wall is bypassed, the distance estimate drops again, and the frontier immediately focuses back onto the goal. Once the goal is reached, the final step is to reconstruct the route through backtracking. To find the shortest route, we shift our focus from the total estimated F-score to the actual G-score, representing the distance walked from the start. Starting at the goal node, we inspect its neighbors and select the one with the lowest G-score. By repeatedly picking the neighbor with the lowest G-score, we trace our way backward until we reach the starting cell. This backtracking reveals the mathematically guaranteed shortest path from the start to the goal. Subscribe for more visual guides on science, coding, and mathematics. Thanks for watching.